Hi, my name's Joe, and this is JoeCoinMining. As a software developer, it is important to understand the key points outlined in the Bitcoin white paper to develop blockchain applications. Here are the 33 key points that you should know. The introduction to Bitcoin in the white paper describes it as a new decentralized electronic cash system. This means that Bitcoin is a digital currency that operates independently of a central authority such as a government or financial institution. Instead, it is based on a decentralized network of computers that collectively verify and validate transactions. This decentralized network is powered by the blockchain, a distributed ledger that records all Bitcoin transactions. The blockchain is made up of a series of blocks, each containing a set of transactions that have been verified and added to the chain through a process called mining. One of the key benefits of Bitcoin as a decentralized electronic cash system is that it allows for fast, secure, and low-cost transactions without the need for intermediaries. Transactions can be sent and received anywhere in the world at any time, without the need for a bank or financial institution to act as an intermediary. Another benefit of Bitcoin as a decentralized electronic cash system is that it is censorship resistant. This means that no one can prevent you from sending or receiving Bitcoin, even if they don't agree with the purpose of the transaction. This is because the network is decentralized and the blockchain is immutable, meaning that once a transaction is confirmed and added to the blockchain, it cannot be reversed or altered. In addition to its benefits as a payment system, Bitcoin has also gained popularity as a store of value and a hedge against inflation. This is because the total supply of Bitcoin is limited to 21 million coins, which makes it a deflationary asset. This is in contrast to fiat currencies, which can be printed by central banks, leading to inflation and devaluation over time. Overall, the introduction to Bitcoin as a decentralized electronic cash system highlights the potential of Bitcoin and the blockchain to revolutionize the way we think about money and financial transactions. As a software developer, understanding the fundamentals of Bitcoin and the blockchain is crucial for building decentralized applications and contributing to the ongoing development of this innovative technology. The second point of the Bitcoin white paper highlights the fact that the Bitcoin network operates as a peer-to-peer network, without relying on a central authority. This means that instead of having a single authority controlling the network and validating transactions, the Bitcoin network is maintained and validated by a decentralized network of nodes. Each node in the Bitcoin network stores a copy of the blockchain, which is a distributed ledger of all Bitcoin transactions. When a new transaction is broadcasted to the network, it is propagated to all the nodes, which then independently verify the transactions before adding it to their local copy of the blockchain. This decentralized approach to network validation has several benefits. First, it eliminates the need for a central authority such as a bank or government to oversee and control the network. Instead, the network is self-regulating and operates based on a set of rules that are agreed upon by all nodes. Second, a P2P network is more resilient to attacks and failures than a centralized network. In a centralized network, a single point of failure could bring down the entire network. However, in a P2P network, the failure of one or several nodes does not affect the overall functioning of the network. Third, a P2P network provides greater privacy and anonymity than a centralized network. Since transactions are validated by a decentralized network of nodes, it is difficult for any single entity to trace a transaction back to its origin or to track the movements of a particular Bitcoin address. Finally, a P2P network allows for faster and more efficient transactions since there is no need for intermediaries or middlemen. Transactions can be broadcasted directly to the network and validated by nodes within seconds, without the need for approval or confirmation from a central authority. Overall, the use of P2P networks is a key aspect of the Bitcoin protocol and the blockchain technology that underpins it. As a software developer, understanding the mechanics of how the Bitcoin network operates as a P2P network is crucial for building decentralized applications and contributing to the ongoing development of this innovative technology. The third point of the Bitcoin white paper describes the limitations of traditional financial systems and how they can be overcome by the use of Bitcoin and the blockchain. Traditional financial systems are typically centralized, meaning that they are controlled by a central authority, such as a government or a financial institution. This centralization can lead to several limitations and problems, including high transaction fees, slow processing times, and the potential for censorship and fraud. For example, in traditional banking systems, transactions often involve multiple intermediaries, such as banks, clearinghouses, and payment processors. Each intermediary charges a fee for their services, which can add up to significant costs for the end user. In addition, transactions can take several days to process, leading to delays and inefficiencies. Another limitation of traditional financial systems is the potential for censorship and fraud, since transactions are controlled by a central authority. That authority has the power to prevent certain transactions from taking place or to alter the record of past transactions. This can lead to corruption and abuse of power, as well as a lack of trust in the system as a whole. Bitcoin and the blockchain aim to overcome these limitations by providing a decentralized peer-to-peer network for transactions. Transactions are validated by a distributed network of nodes without the need for intermediaries or central authorities. This eliminates the need for transaction fees and reducing processing times to a matter of seconds or minutes. In addition, the blockchain is designed to be immutable, meaning that one transaction is recorded on the blockchain, it cannot be altered or deleted. This provides a level of security and transparency that is difficult to achieve in traditional financial systems. Finally, the use of cryptography in Bitcoin and the blockchain ensures that transactions are secure and private. Each user has a public key and a private key, which are used to encrypt and decrypt transactions. This ensures that only intended recipients can access the funds, and that transactions cannot be traced back to the sender without their private key. Overall, the limitations of traditional financial systems have led to growing interest in Bitcoin and the blockchain as an alternative approach to financial transactions, by providing a decentralized, secure, and efficient network for transactions. Bitcoin and the blockchain have the potential to revolutionize the way we think about money and financial systems. The fourth point of the Bitcoin white paper expands on how Bitcoin is designed to overcome the limitations of traditional financial systems. Bitcoin is a decentralized peer-to-peer electronic cash system that allows users to send and receive payments directly without the need for intermediaries or central authorities. This eliminates the high fees and slow processing times that are common in traditional financial systems. In addition, Bitcoin transactions are secured using cryptography, making them highly secure and resistant to fraud. One of the key features of Bitcoin is its use of the blockchain, which is a distributed ledger that records all transactions in a secure and transparent manner. The blockchain allows for a decentralized network of nodes to verify and validate transactions, eliminating the need for a central authority. This makes the system highly resistant to censorship and fraud, as all transactions are recorded and verified by the network. Another advantage of Bitcoin is its finite supply. Unlike traditional currencies, which can be printed or minted at will by central authorities, the total number of Bitcoins is limited to 21 million. This helps to prevent inflation and maintain the value of the currency over time. Bitcoin also offers great privacy and security compared to traditional financial systems. Users can choose to remain anonymous by using pseudonyms instead of real names. The transactions are encrypted using advanced cryptography. This makes it extremely difficult for hackers or other malicious actors to steal funds or compromise the system. In addition, Bitcoin can be used to make international payments quickly and easily, without the need for costly intermediaries or currency conversions. This makes it an attractive option for businesses and individuals who need to make cross-border payments on a regular basis. Overall, Bitcoin represents a major shift in the way we think about money and financial systems by providing a decentralized, secure, and efficient network for transactions. Bitcoin and the blockchain have the potential to disrupt financial systems and offer greater financial freedom and control to individuals and businesses around the world. The fifth point of the Bitcoin white paper focuses on how the Bitcoin network is designed to be a trustless system that relies on cryptographic proof to verify transactions and maintain the integrity of the system. In traditional financial systems, trust is established through intermediaries such as banks and financial institutions. These intermediaries act as trustless third parties that verify and facilitate transactions between parties. However, this reliance on intermediaries comes with several drawbacks, such as high fees, slow processing times, and the risk of fraud or abuse by the intermediaries themselves. Bitcoin, on the other hand, is designed to be a trustless system that relies on cryptographic proof instead of intermediaries. The system uses a public ledger called the blockchain to record all transactions in a secure and transparent manner. Each transaction is verified and validated by a decentralized network of nodes, eliminating the need for a central authority. To ensure the integrity of the system, Bitcoin uses a process called mining. Miners are nodes in the network that perform complex mathematical calculations to validate transactions and add them to the blockchain. In exchange for their work, miners are rewarded with newly minted Bitcoins and transaction fees. The mining process is designed to be difficult and resource intensive, requiring significant amounts of computational power to complete. This is intentional, as it helps to prevent malicious actors from attempting to manipulate the system by spamming the network with fraudulent transactions or attempting to double spend coins. In addition to mining, Bitcoin uses several cryptographic techniques to ensure the security and authenticity of transactions. Each transaction is digitally signed using a private key, which ensures that only the owner of the coins can authorize the transaction. The public nature of the blockchain also makes it easy to verify the authenticity of transactions and prevents double spending. Overall, Bitcoin's trustless system is a major departure from traditional financial systems, which rely on intermediaries to establish trust. By relying on cryptographic proof and a decentralized network of nodes, Bitcoin is able to provide a secure, transparent, and efficient system for financial transactions without the need for intermediaries. The sixth point of the Bitcoin white paper focuses on the transactional nature of the Bitcoin network, describing how transactions are represented as inputs and outputs on the blockchain. In the Bitcoin network, a transaction is defined as the transfer of value from one Bitcoin address to another. Each transaction is a data structure that includes several components, including inputs, outputs, and metadata. Inputs in a Bitcoin transaction refer to the previous transactions that are being spent. When a user wants to send Bitcoin to another user, they must first identify the unspent outputs of the previous transactions that they control, which are also known as UTXOs, unspent transaction outputs. These UTXOs are then used as the input for the new transactions. Outputs in a Bitcoin transaction refer to the new transactions being created. Each output specifies the amount of Bitcoin being spent, as well as the address of the recipient. These outputs become new UTXOs that can be spent in future transactions. Each transaction data includes inputs and outputs, is recorded in a block on the blockchain. Each block contains a set of transactions, which are validated and verified by nodes in the network through the mining process. One of the key benefits of this input-output transactional model is that it allows for greater flexibility and control over how Bitcoin is transferred. For example, a user may have received multiple small amounts of Bitcoin in previous transactions and may want to consolidate them into a single output to simplify future transactions. In addition, this input-output model allows for greater privacy and anonymity in transactions. By using multiple inputs and outputs in a single transaction, it becomes more difficult for outside parties to track the flow of Bitcoin and associate it with specific individuals. Overall, the transactional nature of the Bitcoin network is a crucial component of its design, allowing for flexible, efficient, and secure transfers of value without the need for intermediaries or trusted third parties. The seventh point of the Bitcoin white paper discusses how transactions are verified and validated through the use of digital signatures and cryptographic hash functions. In the Bitcoin network, each transaction is digitally signed by the sender using their private key. This digital signature serves as proof that the sender has authorized the transfer of Bitcoin and prevents any unauthorized changes to the transaction. To verify the authenticity of the digital signature, the recipient can use the sender's public key to decode the signature and confirm that it matches the original transaction data. This process ensures that only the person who controls the private key associated with a Bitcoin address can initiate transactions from that address. In addition to digital signatures, the Bitcoin network uses cryptographic hash functions to ensure the integrity and security of transactions. Each transaction is hashed, meaning it is run through a mathematical algorithm that produces a unique fixed-length string of characters, known as a hash. This hash is then included in the next block in the blockchain, along with the hashes of all previous transactions in that block. This creates a chain of blocks, with each block containing a set of validated and verified transactions that are cryptographically linked together. By including the hash of each transaction in the next block, any attempt to modify a transaction in a previous block would require recalculating the hashes of all the subsequent blocks in the chain, making it computationally infeasible to tamper with past transactions without detection. Overall, the use of digital signatures and cryptographic hash functions in the Bitcoin network provides a secure and trustless way to verify and validate transactions, preventing fraud and ensuring the integrity of the blockchain. The eighth point of the Bitcoin white paper discusses the concept of a timestamp server, which is a critical component of the Bitcoin network that ensures the accuracy and immutability of the blockchain. In the traditional financial system, transactions are typically verified by a central authority, such as a bank or government, which maintains a central ledger that records all transactions. This system is vulnerable to fraud and manipulation, as the central authority can be compromised or corrupt. To solve this problem, Bitcoin uses a decentralized timestamp server that relies on a network of nodes to verify transactions and prevent double spending. This timestamp server is essentially a clock that records the time of each transaction and includes it in the blockchain. When a user initiates a transaction in the Bitcoin network, it is broadcast to all the nodes in the network. Each node then verifies the transaction using digital signatures and cryptographic hash functions and adds it to a block in the blockchain. The timestamp server ensures that each transaction is recorded in the correct order and cannot be altered or deleted. To prevent double spending, which is the act of spending the same Bitcoin twice, the timestamp server checks each transaction against previous transactions in the blockchain to ensure that the user has sufficient funds and has not already spent them elsewhere. By relying on a decentralized timestamp server and a network of nodes to verify transactions, Bitcoin eliminates the need for a central authority and provides a secure and transparent way to transfer funds without the risk of fraud or manipulation. Overall, the timestamp server is a critical component of the Bitcoin network that ensures the accuracy, security, and immutability of the blockchain, making it a trustworthy and reliable means of transferring funds. The ninth point of the Bitcoin white paper discusses the concept of proof of work, which is a key component of the Bitcoin's network's security mechanism. Proof of work is a consensus algorithm that is used to verify and confirm transactions in the blockchain. In the Bitcoin network, every transaction is verified and recorded by a decentralized network of nodes that work together to maintain the blockchain. These nodes compete with each other to validate new transactions and add them to the blockchain, to prevent malicious actors from taking control of the network. The nodes use a proof-of-work algorithm that requires them to solve a complex mathematical problem to validate new transactions. The proof-of-work algorithm used in Bitcoin is called SHA-256, which stands for Secure Hash Algorithm 256-bit. It requires the node to solve a cryptographic puzzle by repeatedly hashing the transaction data until a solution is found. This process is computationally intensive and requires a significant amount of computing power, making it difficult for attackers to manipulate the network. The first node to successfully solve the proof-of-work puzzle earns a reward in the form of new Bitcoins, which incentivizes nodes to continue to participate in the network and validate transactions. This process is known as mining, and the nodes that participate in it are called miners. The proof-of-work algorithm ensures the security of the Bitcoin network by making it prohibitively expensive for attackers to manipulate the blockchain. Since the algorithm requires a significant amount of computing power, an attacker would need to control a majority of the network's computing power to successfully carry out an attack. This is known as a 51% attack. and it is extremely difficult to accomplish due to the decentralized and distributed nature of the network. Overall, proof of work is a crucial component of the Bitcoin network's security mechanism that ensures the integrity and immutability of the blockchain. By requiring nodes to solve a complex mathematical problem to validate transactions, it makes it virtually impossible for malicious actors to take control of the network or manipulate the blockchain. The 10th point of the Bitcoin white paper discusses how network consensus is achieved in the Bitcoin network through the process of mining. Mining is a process by which new Bitcoins are created and transactions are verified and added to the blockchain. In the Bitcoin network, miners are nodes that perform the work of verifying and adding transactions to the blockchain. To do this, they compute with each other to solve complex mathematical puzzles known as proof of work puzzles. The first miner to solve the puzzle earns the right to add the next block of transactions to the blockchain and receives a reward in a form of newly minted Bitcoins. Through this process, the Bitcoin network achieves consensus by ensuring that all transactions are verified and added to the blockchain in a decentralized and trustless manner. This means that no single entity or authority is in control of the network, and all transactions are validated and verified by a distributed network of nodes. The process of mining is crucial to the security and stability of the Bitcoin network. By requiring miners to expend significant amounts of computational power to solve proof-of-work puzzles, the network ensures that malicious actors cannot easily take control of the network. Additionally, because the reward for mining new Bitcoins are built into the protocol, miners are incentivized to participate in the network and work together to maintain its security and integrity. Overall, the process of mining is central to the Bitcoin network's consensus mechanism, enabling it to achieve a high level of security and stability through a decentralized and trustless system of transactions, verifications, and validations. The 11th point of the Bitcoin white paper discusses the incentives for miners to participate in the network through rewards of new Bitcoins and transaction fees. As mentioned previously, mining is the process by which new Bitcoins are created and transactions are verified and added to the blockchain. Miners are incentivized to participate in the network through the rewards they receive for their work. When a miner successfully solves a proof-of-work puzzle and adds a new block of transactions to the blockchain, they are rewarded with a certain amount of newly minted Bitcoins. This reward is currently set at 6.25 Bitcoins per block, but it is halved every 210,000 blocks as a measure to control the inflation of the currency. In addition to the block rewards, miners also receive transaction fees as an incentive to include transactions in the blocks they mine. When a user sends a Bitcoin transaction, they can attach a transaction fee, which is paid to the miner who includes the transaction in the next block. The amount of the transaction fee is determined by the user and varies based on the priority of the transaction. Transactions with higher fees are prioritized by miners and included in blocks more quickly than those with lower fees. This incentivizes users to pay higher fees to ensure that their transactions are processed quickly. Together, these incentives encourage miners to participate in the network, validate transactions, and maintain the security and integrity of the blockchain. The reward system also ensures that the supply of Bitcoins is controlled and that new coins are introduced into the economy at a steady rate. However, the rewards and transaction fees alone may not always be enough to incentivize miners to participate in the network, especially as the number of miners increases and competition for rewards becomes more intense. Therefore, the Bitcoin protocol also includes mechanisms such as mining difficulty adjustments and a limit to the total number of Bitcoins that can be mined to ensure the network remains sustainable over time. The 12th point of the Bitcoin white paper discusses the use of Merkle trees to save disk space while maintaining the integrity of the network. As transactions are added to the blockchain, the amount of data required to store the entire transaction history can become very large. In order to address this issue, the Bitcoin protocol uses a data structure known as a Merkle tree to reduce the amount of disk space required while still ensuring the integrity of the data. A Merkle tree is a binary tree structure in which each leaf node represents a transaction in the blockchain. Each non-leaf node in the tree represents the hash of its two child nodes. The root of the tree represents the overall hash of all transactions in the block. When a new block is added to the blockchain, only the hash of the root node of the Merkle tree is included in the block header. This allows nodes in the network to verify the integrity of the entire block by only downloading a small portion of the data. If a user wants to verify a particular transaction, they can download only the portion of the Merkle tree that contains that transaction, and then verify that the hash of that transaction matches the root hash of the Merkle tree. By using Merkle trees, the Bitcoin protocol is able to reduce the amount of disk space required to store the entire blockchain history, while still maintaining the integrity of the data. This allows nodes in the network to operate more efficiently and makes it easier for new nodes to join the network without having to download and store large amounts of data. The 13th point of the Bitcoin white paper discusses the concept of simplified payment verification, or SPV, which is a method for verifying transactions without the need to download the entire blockchain. The traditional method for verifying transactions in the Bitcoin network involves downloading and storing the entire blockchain, which can be a time-consuming and resource-intensive process. However, not all nodes in the network need to have a complete copy of the blockchain in order to participate in the system. With SPV, a node can verify a transaction by downloading only a portion of the blockchain that includes the block containing the transaction and the block headers of all subsequent blocks. The node then uses the Merkle tree data structure to verify that the transaction is included in the block and that the block is a part of the longest blockchain in the network. SPV nodes rely on full nodes to provide them with block headers and other relevant information. This allows them to verify transactions quickly and efficiently without the need to download and store the entire blockchain. SPV is particularly useful for mobile and lightweight wallets that do not have the storage capacity to download and store the entire blockchain. These wallets can still participate in the Bitcoin network and verify transactions, but they rely on full nodes to provide them with the necessary information. While SPV is a useful tool for simplifying the process of verifying transactions, it is important to note that it is not as secure as a full node that has a complete copy of the blockchain. SPV nodes rely on other nodes in the network to provide them with accurate information, and there is always the possibility of malicious actors providing false information to an SPV node. Therefore, it is recommended that users who require the highest level of security should run a full node and download the entire blockchain. In the Bitcoin network, users can send and receive payments to and from multiple parties through the use of combined and split transactions. A combined transaction allows multiple inputs, i.e., funds from previous transactions, to be combined into a single output, i.e., the payment to a recipient. A split transaction, on the other hand, allows a single input to be split into multiple outputs, each representing a payment to a different recipient. This function enables more complex transactions beyond single one-to-one payments. For example, it allows for payments to be made to multiple recipients simultaneously, as well as for funds to be distributed among multiple parties according to specific conditions. These complex transactions are achieved through the use of script, a simple programming language built into the Bitcoin protocol. The script language enables users to specify conditions that must be met in order for the transaction to be considered valid. For example, a transaction can be set up to only release funds if multiple parties sign off on the transaction, or if a certain amount of time has elapsed since the transaction was created. Combined and split transactions, along with the scripting language, enable a wide range of possible use cases beyond simple peer-to-peer payments. They enable the creation of smart contracts and other innovative applications that leverage the security and decentralized nature of the Bitcoin network. Privacy is a critical limitation of the Bitcoin network that has been a subject of ongoing concern and development. While Bitcoin transactions are pseudonymous, meaning that users are identified by public addresses rather than their real names, the underlying blockchain is transparent and public. This means that anyone can see the details of every transaction that has ever occurred on the network. The lack of privacy can be a significant problem for users who value their financial privacy, as it makes it relatively easy for others to track their spending habits and link them to specific transactions. For example, if a user were to use the same Bitcoin address to receive payments from multiple parties, those parties could potentially link their transactions together and uncover information about the user's spending patterns. To address this limitation, developers have proposed a number of potential solutions, such as adding privacy-enhancing features to the Bitcoin protocol. One such solution is the use of confidential transactions, which allow for the amounts being sent in transactions to be obfuscated. This would make it much more difficult for outside observers to track specific transactions or link them together. Another solution is the use of mixers or tumblers, which essentially shuffle coins between multiple users in order to obfuscate the path of the transaction. This can help break the line between transactions and improve overall privacy on the network. Overall, while privacy remains a limitation of the Bitcoin network, ongoing development efforts are working to address this issue and improve the overall privacy and security of the network. Block structure is an essential aspect of the Bitcoin blockchain. Each block in the blockchain consists of two primary components, a header and a list of transactions. The header of a block contains various pieces of information, including the block's unique identifier, known as its hash, the hash of the previous block in the chain, a timestamp indicating when the block was created, and a nonce, a random number used in the mining process. The list of transactions in a block represents all the transactions that have been confirmed since the previous block was created. Each transaction includes the public addresses of the sender and the recipient, the amount of Bitcoin being transferred, and a digital signature providing the authenticity of the transaction. The block structure is essential because it allows for the creation of an immutable, time-stamped ledger of all Bitcoin transactions. By linking blocks together in a chain, the Bitcoin blockchain ensures that no transaction can be altered or deleted without invalidating subsequent blocks. This structure also enables the use of proof-of-work mining, where miners compete to solve complex cryptographic puzzles to add a new block to the chain. The hash of each block includes the hash of the previous block in the chain, which means that changing any single transaction in a block would require re-mining all subsequent blocks. Overall, the blockchain structure is a crucial component of the Bitcoin blockchain, providing the mechanism for creating a secure, decentralized, and immutable ledger of all Bitcoin transactions. The block header is a data structure that plays a crucial role in the operation of the Bitcoin blockchain. It contains several important pieces of information that are used to secure the network and maintain the integrity of the blockchain. The block header contains a version number that indicates which version of the Bitcoin software was used to create the block. This is important because it allows for backwards compatibility and ensures that older versions of the software can still recognize and validate newer blocks. The block header also contains a timestamp that records the date and time at which the block was created. This information is used to help verify the order of transactions in the blockchain and prevent issues such as double spending. Another key element of the block header is the Merkle root, which is a hash of all of the transactions included in the block. This is a critical piece of information because it enables nodes on the network to quickly verify the contents of a block without having to download and process every individual transaction. The difficulty target is another important component of the block header. This value is used to adjust the difficulty of mining new blocks on the network in order to maintain a consistent block production rate. When the network hash rate increases, the difficulty target is adjusted upwards to make mining new blocks more difficult. Conversely, when the hash rate decreases, the difficulty target is adjusted downwards to make mining new blocks easier. The block header also contains a nonce, which is a random value that miners can adjust in order to try to solve the cryptographic puzzle required to mine a new block. Miners repeatedly change the nonce value until they find a solution that meets the difficulty target, at which point they broadcast the new block to the network for validation. Finally, the block header contains a hash of the previous block header in the blockchain. This is what creates the chain in blockchain. Each block contains a reference to the block that came before it, all the way back to the first block in the chain known as the Genesis block. By including all of this information in the block header, the Bitcoin blockchain is able to achieve a high degree of security and integrity. Nodes on the network can quickly and easily validate new blocks, and the decentralized nature of the blockchain ensures that no single entity can manipulate the blockchain for their own gain. The Genesis block is the very first block in the Bitcoin blockchain. It was created on January 3, 2009 by Satoshi Nakamoto, the creator of Bitcoin. The Genesis block is unique in that it does not reference any previous blocks, and there were no blocks before it. The creation of the Genesis block was an important milestone in the development of Bitcoin, as it marked the birth of the first truly decentralized digital currency. The Genesis block contains a message that refers to a headline in the Times newspaper from that day, which reads, "Chancellor on brink of second bailout for banks." The message in the Genesis block serves as proof of the date and time of the creation of the block. It also reflects the sentiment of the Bitcoin community at the time. The inclusion of this message was an intentional move by Satoshi Nakamoto to make a political statement about the flaws in the traditional financial system and to illustrate the need for a decentralized currency. The Genesis block is also significant because it sets the parameters for the Bitcoin network, including the maximum number of Bitcoins that can be created, 21 million, the time between the blocks, 10 minutes, and the reward for mining the blocks, 50 Bitcoins. These parameters are hard-coded into the Bitcoin software and cannot be changed without a consensus of the network. Overall, the Genesis block is a critical component of the Bitcoin blockchain, and it marks the beginning of a new era in digital currency. The blockchain is a continuously growing list of records, or blocks, that are linked through cryptography in a decentralized network. Each block contains a record of a set of transactions, as well as a header that contains metadata about the block, such as its hash and the hash of the previous block in the chain. The first block in the blockchain, known as the Genesis block, was created by the Bitcoin creator Satoshi Nakamoto on January 3, 2009. This block has a unique characteristic of not having a previous block hash, since there was no prior block in the chain. Instead, the Genesis block is hard-coded with a predetermined hash value. Each block in the blockchain is linked to the previous block through its header, creating an unbreakable chain of blocks. This is achieved through the use of a cryptographic hash function that generates a unique fixed-sized output, or a hash, for any input data. In the case of the blockchain, the hash of the previous block header is included in the current block header, thus forming the link in the chain. By linking blocks in this way, the blockchain creates a distributed ledger of all transactions that have ever taken place in the network. And this ledger is publicly accessible and transparent. This means that anyone can view the complete history of transactions, but the data is secured through cryptographic hashing, making it tamper-evident. In summary, the blockchain is a decentralized and continuously growing list of records, or blocks, that are linked through cryptography, forming an unbreakable chain of blocks. Each block contains a set of transactions and a header that includes metadata about the block and a hash of the previous block header. The blockchain creates a distributed ledger of all transactions that is publicly accessible and transparent, yet tamper evident. In the context of Bitcoin and the blockchain, a hash function is a mathematical function that takes input data of any size and produces an output of fixed size. The output is commonly called a hash or a digest, and it represents a unique digital fingerprint of the input data. One of the key features of a hash function is that it is a one-way function, meaning that it is computationally infeasible to reverse engineer the input data from its hash. Additionally, even a small change in the input data will produce a vastly different hash output. This makes the hash function ideal for ensuring the integrity of data in the Bitcoin network. In the Bitcoin network, hash functions are used in a number of ways. Firstly, they are used in the mining process to solve the proof-of-work puzzles that add new blocks to the blockchain. Miners must find a hash value that meets a specific target, which requires a large amount of computing power and creates a competitive and secure network. Hash functions are also used in the creation of digital signatures, which are used to verify the authenticity of transactions. Each transaction in the Bitcoin network is signed using the private keys of the sender and verified using the public keys associated with that address. The hash of the transaction data is included in the digital signature, ensuring that the transaction cannot be altered or tampered with. Overall, hash functions play a critical role in ensuring the security and integrity of the Bitcoin network by creating unique digital fingerprints of data and making it extremely difficult to tamper with that data. In the context of Bitcoin and the blockchain, a Merkle tree is a data structure used to summarize a large number of transactions in a block. It is also known as a hash tree. The Merkle tree is constructed by taking all the transactions in a block and creating a hash for each one. The hashes are then paired up and hashed again to create a new set of hashes. This process is repeated until there is only one hash left, which is called the Merkle root. The Merkle root is then included in the block header along with other information such as the timestamp and previous block hash. By including the Merkle root in the block header, it is possible to prove that a particular transaction is included in the block without having to include all the transactions in the block. This is useful for a couple of reasons. First, it makes verifying transactions more efficient because it reduces the amount of data that needs to be transmitted and stored. Second, it helps to ensure the integrity of the blockchain by making it difficult for someone to alter a transaction in a block without changing the Merkle root. If the Merkle root changes, then all the subsequent hashes in the tree would also need to be recalculated, which would require a lot of computational power. Overall, the Merkle tree is an important component of the Bitcoin blockchain because it allows for efficient verification of transactions and helps to ensure the security and integrity of the network. The mining process is a critical aspect of the Bitcoin network that ensures the integrity of the blockchain by verifying transactions and adding them to the ledger. The mining process involves solving complex mathematical puzzles using specialized hardware and software known as miners. In order to add a new block to the blockchain, a miner must first gather a set of unconfirmed transactions from the network. These transactions are then assembled into a block, along with some additional data, including a reference to the previous block in the chain. Once the block has been assembled, the miner must solve a cryptographic puzzle, which involves finding a hash value that meets a certain difficulty level. This difficulty level is adjusted by the network every 2016 blocks to maintain a consistent block production rate of approximately 1 block every 10 minutes. The process of finding a valid hash value involves repeatedly running the block's data through a hash algorithm until a hash value is found that meets the difficulty level. This process is computationally intensive and requires a significant amount of processing power, which is why miners often use specialized hardware, known as application-specific integrated circuits, otherwise known as ASICs, to perform this task. Once a miner has found a valid hash value, they broadcast the newly mined block to the network. Other nodes in the network then validate the block's transactions and check that the hash value meets the difficulty level. If the block is valid, it is added to the blockchain and the miner is rewarded with a certain amount of newly minted bitcoins, as well as any transaction fees included in the block. The mining process is a key component of the Bitcoin network, as it ensures that the blockchain remains secure and resistant to attacks. Because miners are incentivized to act in the best interests of the network, they work to prevent double spending attacks or other malicious behaviors that could harm the integrity of the network. Difficulty adjustment is an important concept in the Bitcoin blockchain that helps to maintain a consistent rate of blocks created, which in turn helps to ensure the security and reliability of the network. The difficulty of mining a block is determined by a target value that is set by the Bitcoin protocol. This target value is designed to ensure that it takes approximately 10 minutes to mine a block. The target value is adjusted every 2016 blocks, approximately every 2 weeks, based on the total amount of computational power being used to mine blocks on the network. If the total computational power increases, the target value is adjusted to become more difficult, making it harder to mine a block. Conversely, if the total computational power decreases, the target value is adjusted to become less difficult, making it easier to mine a block. The difficulty adjustment is important because it helps to prevent miners from producing blocks too quickly, which could lead to inflation of the Bitcoin currency. It also helps to ensure that the blockchain is maintained at a consistent rate, which makes it easier to predict when transactions will be confirmed. Overall, the difficulty adjustment mechanism plays a key role in the stability and security of the Bitcoin network, helping to ensure that the network can continue to operate efficiently and effectively over time. Consensus rules refer to a set of rules that all nodes on the Bitcoin network follow to ensure that they agree on the state of the blockchain. These rules help to ensure the security and integrity of the network and prevent malicious actors from attempting to manipulate the blockchain. The consensus rules are enforced by each node on the network and include a range of criteria that must be met for a block to be considered valid. These criteria include 6 elements. Starting with A, block size limit. Each block on the Bitcoin network must not exceed a certain size limit, which is currently set to 1 megabyte. This ensures that blocks can be propagated through the network quickly and efficiently. B, block validation. Each block must be validated by each node on the network to ensure that it meets all of the criteria for a valid block, including the correct proof-of-work valid transactions and adherence to other consensus rules. C, difficulty adjustment. The difficulty of mining new blocks is adjusted periodically to ensure that blocks are created at a consistent rate regardless of changes in the network hash rate. D, block reward. Miners who successfully create a new block are rewarded with newly minted bitcoins, as well as any transaction fees associated with the transactions in the block. The block reward is also subject to consensus rules and changing periodically through a process known as halving. And E, transaction validation. Each transaction on the network must be validated to ensure that it is valid, adheres to the current consensus rules, and does not attempt to spend coins that have already been spent. Now F, consensus mechanism. The consensus mechanism used on the Bitcoin network is proof of work, which requires miners to solve complex mathematical puzzles to create new blocks. This mechanism ensures that no single entity can control the network and that all nodes on the network must agree on the state of the blockchain. By enforcing these consensus rules, the Bitcoin network is able to ensure the security and integrity of the blockchain and prevent malicious actors from attempting to manipulate the network. Additionally, these rules help to ensure that all nodes on the network have a consistent view of the blockchain, which is essential for the network to function effectively as a decentralized payment system. In the context of Bitcoin and blockchain technology, a fork refers to a situation where the network splits into two or more branches, each with a different version of the blockchain. Forks can occur for various reasons, such as software updates, changes to the consensus rules, or disagreements among network participants. There are two types of forks in the blockchain context: hard forks and soft forks. A hard fork occurs when a change to the consensus rules is made, resulting in a new version of the blockchain that is incompatible with the old version. Nodes running the old version will not recognize the new version, and vice versa. This can lead to the creation of a new cryptocurrency if the fork is not resolved, as both branches of the network continue to operate independently. One notable example of a hard fork in Bitcoin's history is the creation of Bitcoin Cash in 2017, which split from the original Bitcoin network to increase the block size limit. A soft fork, on the other hand, occurs when a change to the consensus rules is made, but the new version of the blockchain remains compatible with the old version. This means that nodes running the old version can still recognize the new version, but nodes running the new version may not be able to recognize blocks created by nodes running the old version. Soft forks are typically less contentious than hard forks, as they do not result in a new cryptocurrency being created. An example of a soft fork in Bitcoin's history is the introduction of segregated witnesses, otherwise known as SegWit, which changed the way transaction data is stored in blocks to increase the transaction capacity of the network. Forks can create uncertainty and confusion in the network, as nodes may not know which version of the blockchain to follow. In order to resolve forks, nodes must come to a consensus on which branch of the network to follow. This is typically done by choosing the branch with the most accumulated computational work or the longest chain. Nodes will always follow the longest chain because it represents the most work done by the network, and therefore the most secure and reliable version of the blockchain. In summary, forks in the context of Bitcoin and blockchain technology refer to situations where the network splits into multiple branches due to changes in the consensus rules or disagreements among network participants. Hard forks result in the creation of a new cryptocurrency if not resolved, while soft forks do not. Nodes must come to a consensus on which branch of the network to follow, typically by choosing the branch with the most accumulated computational work. In the context of Bitcoin and blockchain, a soft fork is a change to the Bitcoin protocol that is backwards compatible with the existing rules, meaning that nodes that have not upgraded their software can still participate in the network. Soft forks are used to introduce new consensus rules without breaking existing ones. The mechanism behind a soft fork is to make the rules for blocks validation more strict. Nodes that have not upgraded their software will still recognize the new blocks as valid because they adhere to the existing rules. However, upgraded nodes will now require additional criteria for validating blocks, which makes it harder to create new blocks that are considered valid by the network. For example, one of the most famous soft forks in Bitcoin's history was the implementation of segregated witnesses, otherwise known as SegWit, which happened in 2017. SegWit was introduced to solve the problem of transaction malleability and increase the capacity of the Bitcoin network. The soft fork was achieved by introducing a new rule that required certain data in the transaction to be separated from the transaction signature. This new rule did not break any existing rules, allowed upgraded nodes to recognize blocks that adhered to the new rule. However, it also made it harder for miners to create blocks that were considered valid by the network because they had to follow the new rule. Soft forks are often used when there is a need to introduce a new feature or improvement to the existing protocol, but without causing a hard fork. Hard forks are more disruptive to the network because they require all nodes to upgrade their software in order to remain part of the network. With soft forks, the upgraded nodes can still communicate with non-upgraded nodes, and the network can continue to function normally. In conclusion, soft forks are a way of introducing new consensus rules into a blockchain network without breaking the existing rules. Soft forks allow upgraded nodes to recognize new blocks that adhere to the new rules, while non-upgraded nodes can still participate in the network. Soft forks are a less disruptive alternative to hard forks, which require all nodes to upgrade their software to remain part of the network. In the context of Bitcoin and blockchain, a hard fork is a fundamental change in the consensus rules of the network that results in a permanent split in the blockchain. This means that the new rules implemented in the hard fork are not compatible with the previous versions of the blockchain. And as a result, nodes running the old software will not be able to validate blocks created under the new rules, and vice versa. A hard fork occurs when a significant number of nodes and miners on the network agree to adopt new consensus rules that are not compatible with the existing rules. This can be due to a variety of reasons, such as the need to improve the security or scalability of the network, or to address a critical vulnerability in the protocol. When a hard fork occurs, the blockchain is split into two separate chains, with one chain following old rules and the other following the new rules. Each chain now has its own set of miners, nodes, and users, and both chains are considered valid, independent versions of the blockchain. The introduction of a hard fork can lead to a significant change in the value and usability of the cryptocurrency. Users and investors may need to choose which chain they want to follow, and the market may value one chain over the other, leading to a divergence in price and adoption. One example of a hard fork in the Bitcoin blockchain occurred in August 2017, when a group of developers and miners introduced a new version of the blockchain called Bitcoin Cash. This hard fork was introduced to address the issue of scalability in the Bitcoin network by increasing the block size limit from 1 megabyte to 8 megabytes. This change was not compatible with the existing rules of the Bitcoin network, leading to a permanent split in the blockchain and the creation of two separate cryptocurrencies known as Bitcoin and Bitcoin Cash. Hard forks can be controversial and contentious, as they require significant amounts of agreement and coordination among participants in the network. However, they can also be a necessary means of improving the security and usability of the blockchain, and they provide an opportunity for innovation and experimentation in the cryptocurrency space. A Bitcoin wallet is a software application that enables users to send, receive, and manage their Bitcoin transactions. It functions as a digital wallet that stores the user's private keys, which are necessary for authorizing transactions on the Bitcoin network. Bitcoin wallets come in different forms, each with its own strengths and weaknesses. Some of the most common types of Bitcoin wallets include 4 different types: A. Desktop wallets. These are software applications that are installed on a user's desktop computer. They provide a high level of security as the private keys are stored on the user's computer. However, if the computer is hacked, the private keys could be compromised. Or B. Mobile wallets. These are software applications that are installed on a user's mobile device. They provide convenience and portability as users can make transactions on the go. However, they are less secure than desktop wallets as the private keys are stored on the device, which is more vulnerable to hacking. C. Web wallets. These are online services that allow users to store their private keys on a third-party server. They are convenient and easy to use, but they are less secure than desktop or mobile wallets, as the private keys are stored on a server that is vulnerable to hacking. And D. Hardware wallets. These are physical devices that store users' private keys offline. They are considered the most secure type of wallet as they are not connected to the internet and are immune to hacking attempts. However, they are less convenient than other types of wallets as users must have the physical device with them to make transactions. Regardless of the type of wallet, all Bitcoin wallets have two main functions: sending and receiving Bitcoin transactions. To send Bitcoin, the user must enter the recipient's public address and the amount to be sent. The wallet then creates a transaction and broadcasts it to the Bitcoin network for validation and inclusion in a block. To receive Bitcoin, the user provides the sender with their public address, which is a long string of letters and numbers that uniquely identifies their wallet. When the sender sends Bitcoin to this address, it is added to the user's wallet balance. Bitcoin wallets also typically provide features for managing transactions, such as viewing transaction history, setting transaction fees, and managing multiple addresses. Some wallets also include additional features such as the ability to buy and sell Bitcoin directly from the wallet or to connect to a decentralized exchange. In summary, Bitcoin wallets are essentially tools for managing Bitcoin transactions. They allow users to send and receive Bitcoin, manage their transaction history, and store their private keys securely. Different types of wallets offer varying levels of security and convenience, so users should choose a wallet that best fits their needs and priorities wisely. Public and private keys are a fundamental part of the Bitcoin system and are used to verify transactions and maintain wallet security. In order to send Bitcoin from one wallet to another, a user must have a private key that corresponds to a unique public key associated with the receiving wallet. A public key is a unique identifier that is generated from a private key using a mathematical algorithm. This public key is shared with others to receive Bitcoin transactions. Every public key has a corresponding private key, which is kept secret and never shared with anyone. The private key is used to sign transactions, which allows the network to verify that the sender is the rightful owner of the Bitcoin being sent. In other words, when a user wants to send Bitcoin from their wallet, they must use their private key to sign the transaction. The signature proves to the network that the user is the owner of the Bitcoin being sent and that the transaction is legitimate. The signature is then broadcasted to the network, and the transaction is added to the blockchain once it is validated by the network. It is important to keep private keys secure, as anyone who has access to a private key can spend the Bitcoin associated with the corresponding public key. There are several ways to store private keys, including paper wallets, hardware wallets, and software wallets. These methods offer varying degrees of security and convenience, and it is important for users to carefully consider their options and choose a method that meets their needs. In summary, public and private keys are a critical component of the Bitcoin system, enabling users to send and receive transactions and maintain the security of their wallets. Public keys are shared with others to receive Bitcoin, while private keys are kept secret and used to sign transactions. It is important to keep private keys secure to prevent unauthorized access to Bitcoin holdings. In Bitcoin, a transaction is a message that is broadcast to the network to transfer Bitcoin value from one wallet to another. Transactions are the foundation of the Bitcoin network and are stored on the blockchain, a decentralized public ledger. Transactions are created, signed, and broadcast by the sender using a wallet application and then are validated by the network's nodes through the process of mining. A Bitcoin transaction consists of inputs and outputs. The inputs are the sources of the funds, typically referencing previous transactions that transferred Bitcoin to the sender's wallet. The outputs are the destinations of the funds, typically identifying the receiving wallet addresses and the amount of Bitcoin to be transferred. Each transaction also includes a transaction fee paid by the sender to incentivize miners to include the transaction in the next block. Transactions in Bitcoin are verified and validated using digital signatures and cryptographic hash functions. When a transaction is created, the sender signs the transaction using their private key, which is a unique identifier that only they possess. The digital signature ensures that the transaction cannot be modified or tampered with by anyone other than the sender. Once the transaction is signed, it is broadcast to the Bitcoin network, where it is verified and validated by the network's nodes. The nodes use cryptographic hash functions to verify that the transaction is valid and that the sender has sufficient funds to complete the transaction. The transaction is then added to the mempool, a pool of unconfirmed transactions waiting to be included in the next block. Miners are responsible for creating new blocks and adding transactions to the blockchain. To add a transaction to a block, a miner must first solve a complex mathematical puzzle known as proof of work. This puzzle requires significant computational resources, and the first miner to solve the puzzle earns a block reward, currently set at 6.25 bitcoins, as well as the transaction fees associated with the transactions included in the block. Once a block is created, it is broadcast to the network, and the nodes verify the transactions in the block. Once the block is confirmed by a majority of the nodes on the network, it is added to the blockchain, and the transactions it contains are considered confirmed. Overall, transactions are a critical component of the Bitcoin network, enabling users to transfer value securely and quickly across the world through the use of digital signatures, cryptographic hash functions, and the mining process. Transactions in Bitcoin are validated and confirmed, ensuring the integrity of the network and the safety of its users. Transaction fees are a crucial component of the Bitcoin network that help incentivize miners to include transactions in new blocks. When a user wants to send a Bitcoin transaction, they typically specify a transaction fee that they are willing to pay to miners to prioritize their transaction over others waiting to be processed. Miners are incentivized to include transactions in new blocks because they receive two types of rewards for doing so: block rewards and transaction fees. Block rewards are a fixed amount of new Bitcoin that are created with each new block and are currently set at 6.25 BTC. Transaction fees, on the other hand, are variable and are determined by the market supply and demand for block space. In general, higher transaction fees mean that a transaction is more likely to be included in the next block, while lower transaction fees mean that a transaction may take longer to be processed. Transaction fees are typically calculated based on the size of a transaction in bytes, rather than its monetary value. This is because larger transactions require more data to be stored on the blockchain and take up more space in each block. The current average transaction fee on the Bitcoin network is around 30 satoshis per byte, or roughly 20 USD at current Bitcoin prices. Transaction fees are paid by the sender of a transaction and are collected by the miner who includes a transaction in a new block. Miners prioritize transactions based on the fee they offer, with higher fee transactions being included first. In this way, transaction fees serve as a market-based mechanism for determining the order in which transactions are processed and the overall speed of the Bitcoin network. Transaction fees are an important aspect of the Bitcoin network because they help ensure that miners are incentivized to continue verifying transactions and maintaining the security of the network. Without transaction fees, miners would have little reason to prioritize one transaction over another, and the network would become congested and slow. By incentivizing miners to prioritize higher fee transactions, the Bitcoin network is able to maintain a fast and reliable payment system that can process transactions around the world in a matter of minutes. Double spending is a problem that has long plagued traditional electronic cash systems, in which an individual can send the same digital currency unit to multiple recipients, effectively spending the same money twice. This is a problem because it undermines the integrity and trust of the currency, as it can lead to fraudulent transactions and a lack of confidence in the system. Bitcoin solves the double spending problem through the use of cryptographic proof and the blockchain. Each transaction on the Bitcoin network is recorded on a public ledger called a blockchain, which is maintained by a distributed network of nodes that verify and confirm transactions. In order for a transaction to be confirmed and added to the blockchain, it must be verified by a network of miners through a process called mining. Mining involves solving complex cryptographic puzzles that require a significant amount of computational power. When a miner successfully solves a puzzle, they are rewarded with newly minted bitcoins and transaction fees from the transactions they include in the block they just mined. This incentivizes miners to verify transactions and add them to the blockchain. The double spending problem is addressed by the fact that once a transaction is confirmed and added to the blockchain, it becomes an immutable record of the transfer of funds from one wallet to another. Once a transaction is recorded on the blockchain, it cannot be reversed or altered, ensuring that each Bitcoin unit can only be spent once. Additionally, each transaction on the Bitcoin network is verified using a public key cryptography system. Each Bitcoin wallet has a unique public key and a corresponding private key. The private key is used to sign transactions, which are then verified using the corresponding public key. This ensures that only the owner of the private key can initiate a transaction, preventing unauthorized spending of Bitcoin. In summary, the use of cryptographic proof, the blockchain, and public key cryptography in Bitcoin ensures that the double spending problem is effectively solved, creating a secure and reliable system of electronic cash. Bitcoin has the potential to disrupt traditional financial systems in several ways. First and foremost, Bitcoin is decentralized, meaning that it is not controlled by any central authority like a government or a financial institution. This decentralization allows for greater financial freedom and autonomy, as users can transact without needing to go through a central authority. Additionally, Bitcoin is based on blockchain technology, which provides an immutable and transparent ledger of all transactions. This transparency could potentially lead to increased trust between parties and decreased reliance on intermediaries like banks and financial institutions. Moreover, the blockchain's ability to facilitate secure and tamper-proof transactions has the potential to reduce fraud and corruption in the financial sector. Another potential disruption lies in Bitcoin's ability to facilitate cross-border transactions with lower fees and faster processing times than additional financial systems. This could be particularly beneficial for individuals and businesses that regularly engage in international trade, as they may currently face high fees and long processing times when using traditional financial systems. Furthermore, Bitcoin's ability to facilitate micropayments could open up new opportunities for innovation and commerce. Micropayments are transactions involving small amounts of money, often fractions of a cent, and are currently not feasible with traditional financial systems due to high transaction fees. However, with Bitcoin, micropayments can be processed quickly and cheaply, potentially enabling new business models and revenue streams. However, there are also potential risks and challenges associated with the disruption that Bitcoin may bring. For example, the lack of regulation and oversight in the Bitcoin space could lead to increased volatility and instability. Moreover, the potential for illegal activities such as money laundering and terrorism financing is a concern. Overall, while there are risks and challenges associated with the disruption that Bitcoin may bring, there is also significant potential for innovation and financial freedom. As the technology continues to evolve and mature, it will be interesting to see how it impacts traditional financial systems and creates new opportunities for individuals and businesses alike. Understanding these 33 points is crucial for any software developer looking to work with the Bitcoin network or develop blockchain applications. By understanding these 33 points, software developers can gain a comprehensive understanding of how the Bitcoin network operates and how to develop blockchain applications that utilize its unique features. From the basics of blockchain and cryptography to the intricacies of mining and network consensus, these concepts provide a solid foundation for building applications that leverage the power of Bitcoin and the blockchain. Thanks for listening. Have a wonderful day.